Hey, in this video I'm going to show you how to use the CT Recon FTK Astra repository that I'm hosting on my GitHub. This is the first video in a series, and it's actually going to be about CT calibration correction with the epipolar consistency conditions. But it makes a lot of sense to first set up the CT Recon FTK Astra repository because you will be needing reconstruction and also 3D image viewing. So I'm just going to be showing you how to use this. Now, first of all, I already cloned this from GitHub, and I'm just going to do the install here. To do this, I'm going to create a virtual environment called Recon, and I'm going to do pip install with the GUI, that's the graphical user interface option. So now this is going to install not only the command line tool that is doing the actual reconstruction, but it's also installing a 3D viewer, which is simple but very useful. It compares 3D images of the same size, and also a reconstruction GUI, which is basically what this video is about. So I'm going to just run this reconstruction graphical user interface, and it actually comes with this beautiful dialog that allows you to load example data. Now, if you have CT data already, you may have a reconstruction JSON file that you can just open, or you want to define your own trajectory. You just select the images and then you define typical parameters of a circular trajectory. So it also supports this. But we're just going to go with the sample data. And the reconstruction GUI looks like the following. First of all, on the left-hand side, you have a JSON editor. This command line tool doesn't do much other than visualize a trajectory, allowing you to set or define what is in this JSON file and then just pass it to the command line tool. The JSON file is going to be saved in this path, and you have this little directory button here that reveals the files in Explorer. Now, for the purpose of this video, I'm just gonna do a reconstruction here. Now, first of all, the visualization in the middle is going to show you the source trajectory, which is the teal circle, and the trajectory of the detector centers, which is the black one. And this is not the typical CT scan. You can see that in this case the detector is very close to the object. If you think about micro CT, for example, the object might be very small here and the detector very far away by comparison. Next, it shows you the isocenter, which is the world coordinate system also, and this yellow dashed line, which is the rotation center. It also shows you a reconstruction cylinder, which is this orange thing in the middle. This is the minimum circumscribed cylinder around John's quadric, if you're familiar with it. This is basically the region of space that is actually going to be properly reconstructed. Finally, it shows you the detector, and it is given you by the v-axis, that's the vertical, and the u-axis, that's the horizontal detector axis, plus this, well, green transparent cube, which is the reconstruction volume. So in this example, I set it up to fully project to the detector so that it becomes clear what it does. If I'm projecting this green cube to the detector, I get these red lines. The visualization actually shows you just one of the images, and you can change the particular view by moving this visualization slider. Now, as you can see, it's currently simulating a turntable. This is different from how the data is actually stored, because projection matrices are usually stored as modeling the projection from a 3D space that is fixed in the volume coordinate center and how it projects 2 pixels on the detector. This is stored in the OMPL, which is just short for one matrix per line file. This is a simple text format. I'm going to show it to you. It's something I came up with, so nothing special, but it stores the spacing as well as the detector size in special fields, and then just contains one matrix that is 3 by 4, 1, 2, 3, 4, no, 3, 1, 2, 3, 4, semicolon, 1, 2, 3, 4, another semicolon, and so on. Yeah, so for example, this is normalized, so this is the principal ray. You can see it's pointing in the negative x direction in the first matrix. And this, if this is normalized to 1, which it is actually giving you the distance from the source to the isocenter. So the rest of the matrix is probably clear to you. Anyway, knowing the pixel spacing, you can visualize it in this manner. So that's what's happening. You can also view this whole thing as a gantry coordinate system. So this is actually closer to what the matrices encode. In this case, source and detector rotate around the object, and this is how the matrices are actually encoded. The volume will just stay fixed. And last but not least, you can also view projection view, see this entire scene from the point of view of the X-ray source. This is jittering a little bit. If you are loading your own TIFF files from 2D files, you can also preview the image data here, which is currently not working because I didn't implement it for 3D stacks of images. But this is very useful if you want to check, for example, rotation direction and such things. The tool also gives you some useful information. For example, it computes the mean source isocenter distance, source detector distances, and it also computes the isocenter as the closest point to the back projection rays of the center pixel of all detectors. And it also extracts the plane of rotation. This is the source plane, and the normal is going to be used as the rotation axis here in yellow. Finally, very important function, it allows you to define the reconstruction volume. You can move it, for example here, that's just moving the thing around. Yeah, you can also do that with a mouse probably. Just moving. You can automatically center it with the center button. This is just going to center the volume in the isocenter. You can even rotate if you feel like it, but probably more importantly, you can use any of the automatic buttons down here, which will, well, this is a little awkward, yeah, which will give you the inscribed axis-aligned bounding box, oriented bounding box, if you have a narrow volume, for example, this may make sense, but also axis-aligned bounding box around the, oh, inscribed, sorry, I've confused this. This is the axis-aligned box, this is inscribed in John's conic, and this is the inscription of the oriented box in the same conic, you can see that here. Yeah. And these are the more typical ones, the axis-aligned bounding box and the oriented bounding box. Finally, actually the most common one that you will be using is the minimum circumscribed cylinder. So this is using John's quadric that is here shown in orange, and it's gonna map a cylinder around it in the direction of the rotation axis, and finally add a bounding box. So this is the most typical, yeah, at least for circular trajectories that you want to do. Right. Finally, there's one more function that's worth mentioning. You have this rescale function. For example, if you feel like 500 pixels, voxels in each dimension just isn't enough, you can upscale by a factor of 2 and just rescale. It's going to double the pixel, the voxel dimensions, and it's not going to move the red, the green box at all. There you go. Now we have a huge volume. Or we can go back to what it was by this. Right, let's just default. And finally, we can select a reconstruction kernel. For the sake of this demo, I'm going to do Shep Logan. We can also change the cylinder size a bit if you want to cut out more pixels. If you're giving a value other than 0 here, it's actually going to mask out all voxels that are not inside this orange cylinder. Hit reconstruct. Oh, I already created this file, so it's asking me whether to replace or rename. I'm just going to replace it. And then it's running the command line tool with the JSON we just defined. This is the result. The viewer is very practical. It gives you the option to scroll through the volume, obviously, but also zoom and move very easily. And with right-click and drag, you can define a box, and auto contrast will be applied to the voxels that are inside of this box, so you can focus on specific intensity ranges if you want. Right, you can also change the slicing, obviously. But the most important feature of this tool that we'll be using for calibration correction later, if we load the example dataset again, and just for the sake of it, I'm going to do a ramlag, so hard kernel reconstruction as well. Going to change the name of the file, and I'm just going to hit reconstruct again. Now the cool thing is that we've just created two nerd volumes in the same directory, and the software understands this and automatically adds both of them in the viewer. So now you can just switch between them with this pop-down menu or with the keys 1 and 2 on your keyboard. It doesn't look very different at this zoom level, but I'm just gonna go very close and probably also window a little bit, and then you probably see the differences in sharpness of the reconstructions with the two kernels. So what we'll be using in the next video is different calibration correction technologies, and we're going to be comparing them in this manner. So that's what this video was actually for. I hope to see you again, and thank you very much.